Hello and welcome to the AICE Chemistry lecture series. In this video, we're going to start chapter 15, which is the first organic chemistry chapter that's going to address a specific functional group. And in this case, the specific functional group, although it's not really a functional group, is the hydrocarbons. We're going to look at all the compounds that are made out of just carbon and hydrogen, are all the intricacies that come with them, and their chemical reactions, so on and so forth. So let's get started. Now, looking at this chapter, we're going to have 6 different sections that we're going to go through. We're going to start every chapter moving forward from now on with a look at the homologous group of that specific functional groups. In this particular example, we're going to look at the homologous group of alkanes. So basically, what is an alkane? What does it look like? Nomenclature. We're going to very quickly go over all the things about alkanes that we saw in chapter 14. We're then going to go into the reactions. So we're going to start section 2, with how alkanes react. Then we're going to move on to a different type of hydrocarbon, because remember, there are multiple different types of hydrocarbons, which are the alkenes in section 3. We're going to look in section 4 at the specific oxidation reactions of alkenes. And then in section 5, we're going to see how addition polymerization can happen, which is the making of polymers from alkenes. Finally, in section 6, we're going to look at specific questions regarding polymers that might appear in the AICE exam, because it's a very niche topic for the AICE chemistry exam, has some very unique questions. But let's start with section 1. Let's start with the homologous groups of alkanes. Now, if we remember from our prior example, or our prior chapter, homologous groups or homologous series are just a series of chemicals that have increasing number of carbons but the exact same functional group. So for alkanes, these are just basic hydrocarbons made out of carbon and hydrogen that have all single bonds and just have more and more carbons. So methane being the simplest one, and then moving on to ethane with 2 carbons, then propane with 3 carbons, so on and so forth. So this is especially easy to see in the skeletal formula, because we go from ethane to propane to butane by just adding more and more carbons to the chain. So let's look at what we need to grasp as sort of basics for alkanes. Alkanes are, if you remember from chapter 14, the hydrocarbons that are all single bonded, meaning that we have a series of carbons made out, a carbon chain made out of nothing but carbon and hydrogen and single bonds. Most alkanes come from crude oil, meaning that this is the oil that we drill from the earth, and that crude oil is a mixture of hydrocarbons, most of which are alkanes. We process crude oil and separate it into its individual components through a process called fractioning. We're going to look at fractioning in the next slide. But like I said, crude oil, what we call oil, is a mixture of hydrocarbons, a mixture of a lot of different compounds made out of carbon and hydrogen. When we separate them, that's when we can isolate things like butane and propane and hexane and so on and so forth. Now, all alkanes are going to have the same general formula because they're all made out of just carbon and hydrogen single bonded. They all have the same general formula of CnH2n plus 2. So if an alkane has 1 carbon, like methane, then it will have 4 hydrogens, because if n is 1, 2n, 2 times 1 is 2, plus 2 is 4. If you have 2 carbons in an alkane, then that alkane will have 6 hydrogens, because 2 times 2 plus 2 is 6. If an alkane has 6 carbons, then it will have 14 hydrogens, because 2 times 6, n being 6 here, plus 2 is 14. So that's always going to be the general formula for an alkane because they're so single bonded, they're very simple to predict. In an alkane, each carbon is going to be sp3 hybridized because each carbon is only single bonded. It's going to have 4 bonds. And so every one of those carbons will have an sp3 hybridization and have this tetrahedral structure. So we can see that here. I'm going to try to draw in 3 dimensions, although I'm very bad at it. We can see that here, this tetrahedral structure that each one of the carbons has in an alkane. They're all tetrahedral, they're all sp3 hybridized, and therefore every one of these bond angles is 109.5 degrees. That means that they're going to contain the maximum number of hydrocarbons that we can possibly have, or hydrogens on the carbons that we can possibly have. That's why a lot of the time alkanes specifically are known as saturated hydrocarbons. They're saturated with hydrogen. They have the most carbon that they can possibly hold. So just be aware that anytime you hear the word saturated hydrocarbon, what this means is an alkane because it's a hydrocarbon that has the most hydrogens possible on the carbons. And so it's saturated with hydrogen. All right? So let's look at how we get these alkanes from crude oil. Because believe it or not, this is part of your curriculum. This might seem very niche, but you are supposed to have a basic understanding of where these chemicals come from, not just what they are. So crude oil and crude oil processing is found or is done in processing plants all over the world. We have many in the US, and we process crude oil that we import from other countries. Crude oil is found trapped in layers of rock beneath the earth. Essentially, things a really long time ago died. Those things slowly, through pressure and high temperatures, have broken down over time, and they have become the soup of alkanes, cycloalkanes, and other benzene-containing compounds. So crude oil is just that. It's a soup of chemicals. It's a soup of carbon and hydrogen-based chemicals with a few other things. Some might have a little sulfur here and there, or a little nitrogen here and there, or oxygen. But for the most part, it's just hydrocarbons. Alkanes, cycloalkanes, a few alkenes, but not many. Some aromatic compounds. All of this from really, really long dead dinosaurs and plants and whatnot. In order to use crude oil, we can't use it just as it is. Because crude oil, like I said, it's a mixture of hydrocarbons, right? And let's put that up here so we can remember it, keep remembering it. Crude oil is a mixture of hydrocarbons. So how do we process crude oil? We are going to separate crude oil into what we call fractions, which are mixtures of different hydrocarbons with very similar boiling points. All hydrocarbons are very volatile, meaning that they can, for the most part, be vaporized really easily. So we take advantage of that and how they have different boiling points. What essentially happens is that we're going to grab this crude oil, we're going to heat it up really, really, really hot. We're going to pump that through a heating element that you see here. And when the crude oil comes out, this side is very, very hot. Let me use a different color. It's very, very hot down here. Let me use red for this. At the bottom. And so most of those crude oils here, or most of those chemicals here, are going to be in the gas state. Some of them are still going to be liquid, and the ones that are liquid are going to essentially come out the bottom and drip out the bottom, and they're used for things like making plastics and whatnot. And then steam is pumped in, really hot steam is pumped in to this, what we call fractioning column. The fractioning column is the mechanism through which fractioning happens. It's a column which has a really hot steam being pumped through the bottom, And so all of these gases, all of these parts of the crude oil are going to become gases, and they're going to rise because they're in the gas state, and they're going to follow the steam up. While that goes up, what happens is that the fractioning column is a lot colder at the top than it is at the bottom. As this mixture of gases rises with the steam, they start to cool down. So as they go through the different fractions of the fractioning column, those gases cool down. So let's say, and I'm going to use random numbers here, don't quote me on these numbers, but let's say if it's 300 degrees Celsius down here, then halfway through maybe 150 degrees Celsius. And then up here maybe at room temperature 25 degrees Celsius. And so you have everything in between. Maybe here's a 200 degrees Celsius, and here's a 100 degrees Celsius. So as these gases rise through the column, through the different what we call fractions, some of these chemicals reach their condensation point, and they'll come out as a liquid as they hit their condensation points. The different parts of the crude oil have different condensation points. So maybe here you'll get one liquid, and then a different liquid down here, and a different liquid up here. As we go and these different components of crude oil cool down, they are removed because they liquefy, they condense. So we have things like heavy gas oils here. Gas oil and diesel are more in the top. Some things like raw gasoline that we put in our cars, or things like methane and butane that we use for lighters, are up here at the top because they stay gases. Kerosene's a little lighter than gas oils. So why does this happen? We learned about intermolecular forces already. We know that the London dispersion forces that alkanes feel, because they are non-polar alkanes, are going to increase. Actually, let me use arrows. So the London dispersion forces that alkanes feel are going to increase with increasing number of electrons, which is equivalent to increasing molar mass. So what happens here? The smaller hydrocarbons, things like CH4 and C2H6, those are going to have much lower boiling points. They're going to be gases at the top. Whereas the much larger hydrocarbons are going to liquefy a lot sooner because the London dispersion forces are stronger. So the smaller hydrocarbons are more volatile, and that's a word we use, and a word you should be familiar with and start being familiar with. They're going to be more volatile, meaning they're going to have much lower boiling points. So let's put that here. So volatile, oops, that's a very big pencil there. Volatile means lower boiling point. And so things up here are going to be things that are volatile, things like CH4 and C2H6, things that are very light, because they're going to liquefy at much higher temperatures. Some of these, in fact, methane is a gas even at room temperature. On the other hand, in the bottom, you're going to have things that are not volatile. So things like, let's say C10H22 will be down here. These are not as volatile, and so they're going to have much higher boiling points. So the bigger compounds, the bigger molecules are going to come out and liquefy in a lower temperature, whereas the much smaller molecules, which much lower London dispersion forces, are going to come out at the top when it's cooler. And that's how fractioning works. This is where most of our commercially available alkanes come from. So the gas you pump into your car, the butane in your lighters, the jet fuel that we use to fly airplanes. Even this residue is going to be a lot of the alkanes that we use to make plastics are going to come from there. So just think about this. This is a quick lesson on how crude oil chemistry works. Very, very lucrative field in chemistry. Some of the highest paid chemists are crude oil chemists, or oil chemists. So yeah, this is essentially how fractioning works, through a fractioning column. It's a way of separating all the different hydrocarbons and alkanes that make up crude oil by their boiling point by using this fractioning column. So that's it. That's it for section 1. Again, it's just an introduction to alkanes and hydrocarbons, and then in the next section, in the next video, we're going to start to look at what are the different chemical reactions that these alkanes can undergo, which, foreshadowing, is not many. It's only 2 reactions. But I will see you all in the next video to discuss that. Until then, see ya next time.